All right, so thank you guys so much for getting up early and coming out to see this talk. I'm going to talk today about, I'm going to give you guys an introduction to the JPL flight software product line. If you remember the past, I think it was either the past, last year's flight software workshop, I talked about MSL and the evolution of the Mars Science Laboratory flight software architecture in general. And so what I'm really going to be talking about today is kind of the next step in that evolution, okay? Taking our code base, mining our assets to come up with an actual JPL flight software product line. So I'm going to talk about what is the motivation and objectives of a product line. What is the JPL flight software product line? What does it actually consist of? What are the different parts of it? I'll talk about product line development and evolution, and then we'll actually get into the meat of the presentation, which is the actual software architecture itself, the product line architecture. Before I get started, though, I want to acknowledge the team. This is really a crackpot group of software engineers. Crackpot group of software engineers. This is kind of we're actually referring to the software as the core JPL flight software core, and I'll be honest with you, this group of engineers is really the JPL flight software core group of software engineers. So Ben Sitchie, who's actually no longer at JPL, he's a contractor working for Goddard, Dr. Dan Gaines, Dr. Ed Gamble, Dee Liang, Jeff Levison, Dr. Rajiv Joshi, Lloyd Manglapus, Steve Scangor, and Igor Uchenik. These folks did a tremendous job on MSL, and we carried their experience forward for the JPL flight software product line, so I wouldn't be doing due diligence without acknowledging their hard work and effort into formulating this new strategy of software engineering at JPL. So let me give you a little background and motivation about the product line itself. So as many of you might know, our heritage flight software is comprised of very tightly coupled modules integrated into a monolithic delivery, a very large monolithic delivery that is meant for a specific mission and is tied to the flight system on which that software is deployed, with very limited reuse across projects. As Gerard mentioned yesterday, he gave you kind of the scope of the size of the MSL flight software. MSL flight software is approximately 3 million lines of code. This was a huge monolithic flight software delivery. And starting as early as Pathfinder, this flight software from one project to the next have followed this kind of clone and own philosophy of reuse, where instead of a more rigorous reuse approach, the subsequent project literally takes the flight software from the previous project and then starts massaging it into the flight software appropriate for the next deployment. And as you can imagine, this is extremely difficult to do, error-prone, and actually really results in a very limited amount of reuse. So recently, there has been this effort within Division 34, which is our avionics division, to create something called a reference bus, which is basically a standard set of hardware boards and pieces of hardware that are meant to be kind of the catalog from which a project develops the deployment environment for the flight software on the next mission. So basically, for a particular flight system, you go to this reference bus and you can pick out which boards and which computer and what kind of configuration you want. And so this really arose from this desire to have a coherent approach to developing avionics platforms from mission to mission. And if you think of avionics in the big A sense, right, that it includes both the hardware and the software, you realize that you actually also then need a coherent approach for the associated flight software implementation to sit on top of that reference bus hardware. So there was definitely identified a need for a reusable flight software base. So Reference Bus as a project then commissioned the development of a JPL flight software product line by Section 349 last year in FY13. And the objectives are pretty straightforward: to facilitate the delivery of integrated avionics and flight software product to projects. So the idea being that you go to this reference bus, you pick out your set of your avionics suite for a particular mission, and then you get the flight software associated with that avionics as an integrated, coherent package. We want to significantly improve the reuse potential for flight software while leveraging existing flight-proven implementation approaches and assets. So instead of a clone and own model of reuse, a more rigorous form of reuse, but we also recognize that we have a very expensive piece of flight software in the MSL code base that we want to leverage for use in this product line. So we want to mine that MSL code base for assets as well. We'd like to reduce the startup time and cost for flight software infrastructure development on a project or task. Seems pretty straightforward. Facilitate software technology infusion that enhances the applicability and the reliability of the flight software assets and maintains visibility of the product line. So previously it was very difficult, especially in this clone and own mode of operation, to actually infuse new technologies into the flight software. Most of the development effort is spent on tailoring this old software to the new deployment environment. So if we can actually construct a means by which we can do technology infusion, then we are actually starting to get new technologies into deployments on subsequent missions. And finally, facilitate a collaborative flight software development environment where the line and the project can be organized around distributed development and delivery of flight software capabilities. So as I was saying before, we have this very large monolithic flight software build, and oftentimes the architecture of the team that is building the flight software matches the architecture of the flight software product itself. So not only did we have a very large monolithic flight software build, we had a very large monolithic flight software team. On MSL, we had at any given point in time between 35 and 50 developers working on the MSL flight software, and they were all under the management of a single cognizant engineer, that was Ben Sitchie. And it becomes extremely difficult to manage and to keep track of all those developers and what they're doing. So if we can create an approach and an architecture that supports a more distributed flight software development strategy, we'd like to follow that as well. So what was our solution? We decided to create a JPL flight software product line. And it's important to really characterize, what is different about a product line as opposed to a typical clone and own reuse pattern. And I think that the difference with the flight software product line comes down to really the fact that there are three main activities that are involved in fielding a successful flight software product line. So first and foremost, a product line is a collection of reusable flight software assets for deployment on a wide range of flight projects. So think of a car manufacturer, right? You have a whole catalog of pieces of the car that can be assembled in different ways to create a different model. For example, kind of a classic example used is that the Ford Taurus and a Jaguar actually have the exact same chassis underneath, right? But depending on what else you put on top of that chassis, you actually get a different product in the end. So that's kind of the classic example of having a core asset base and then assembling products from that core asset base. So our goal is to target a wide range of missions, from discovery, new frontiers, big flagship missions like MSL and Europa, as well as small-scale satellites. The product line is also a product development strategy. So the idea being that you have this group of assets, but then you also have guidelines and a strategy for developing these products, right? So this includes things like architectural guidelines and well-defined interfaces so that projects can integrate this mission-specific flight software pieces together to create a complete flight software system. So it's important to know that these assets include things like requirements, checklists, processes, people, training. It's not just about reusing the flight software code itself. It's about reusing all of the infrastructure that is needed to actually develop a product. And finally, and I think it's worth noting that this may be the most important activity in fielding a successful flight software product line. And in fact, in much of the flight software product line literature, this is called out as basically, if you're not able to accomplish this, you will not be able to field a successful product line. And that's the management approach. You absolutely have to have support of your management and your organizational structure in order to actually make the product line successful. So we are shifting to a model where the line actually owns the product line assets themselves and oversees their proposed use, deployment, maintenance, and evolution. So they're going to be providing the configuration control of the product line assets and defining the process for asset deployment and overall flight software system integration. So we're taking the responsibility of the actual flight software product out of the project context and making it the responsibility of the line organization. That's a huge cultural and paradigm shift at JPL, and we believe that this is key to the success of the JPL flight software product line. So what are the benefits of the flight software product line? I think they're really tied to the objectives. It's kind of funny that you have this problem statement, you have your project objectives, what do you want to accomplish? And looking at those, it was like, a no-brainer. Well, a flight software product line is the way to go. And that's because the proposal teams, for example, can leverage assets to meet a flight software system specification and cost. So your flight software costs are decreasing as this asset base grows. So it's really, you see your return on investment through economies of scale. So as the assets are used over more, as the product line is leveraged over more and more missions, you really start to see your return on investment because the assets become more solid and you are adding to your asset base and applying to a more wide variety of products. As I mentioned before, the flight software line actually manages the asset base. So this is going to minimize differentiation by projects and reducing overall implementation costs. Projects have a culture and a tendency at JPL to reinvent the wheel, to do it their own way, to grow their own products. If we can have a centralized management of assets under the line organization, we're standardizing the product that is used across every project. So that's really going to help reduce overall implementation costs because they don't have to be tailored as much to each mission. And also it's a coherent approach to supporting different reference bus configurations, if all the future projects are utilizing reference bus assets, then in the same respect, they're utilizing the flight software assets, thereby kind of standardizing the approach and making it more intellectually manageable for the flight software developers and flight software coggies on the different projects to actually use these assets. The architecture itself, the product line architecture, which we'll be talking about shortly, standardizes interfaces and patterns for subsystem organization to deliver flight software. This is the big one. This enables distributed flight software development. So instead of this huge monolithic flight software team, because you have a standardized architecture and a standardized set of interfaces, what you can actually do is you can farm out pieces of your flight software to the actual subsystem delivery organizations. So no longer do we have GNC representatives on this big flight software monolithic team. The GNC subsystem actually delivers its hardware and its software together, okay? And so this enables more distributed flight software development with more coggies being responsible for their target subsystems. This also enables distributed flight software development across multiple organizations. So kind of the gold standard where we want to go is to be able to actually integrate flight software delivered by other organizations like APL, for example. One of the big missions we're working on right now is Europa, and there's going to be a split in the flight software between JPL and APL. And this is going to facilitate the ease of integration of those flight software pieces into the system. It also supports an iterative approach to asset development. So this is what we were talking about earlier, this technology infusion and evolving strategic vision of the line. So as the strategic vision of the line organization evolves, we want to make sure that the product line is evolving as well. If a product line doesn't evolve, it's going to die, right? It can't just be a snapshot in time. It must evolve as technology evolves and as our strategic vision evolves. So by developing these assets incrementally and iteratively over time, we can actually infuse the new technologies and store them in our asset base for use on future missions. And as I said before, it aligns nicely with this idea of a reference bus product delivery paradigm. So I mentioned before that kind of the success or failure of the JPL flight software product line really hinges on the Section 349 organization and the line organization. And so we've actually reorganized our section. Section 349 is avionics and flight software. We've actually reorganized in order to support this line organization owned product line. So the core flight software group maintains the product line and hosts the development team. So let's see if I can. So you see here we have the flight electronics and software systems section 349 with the section management. And Jim Donaldson, he gets his special box right here. He's right there. And then we have 3 different flight software groups. We have the core flight software group here, which maintains the product line and hosts the development team, so they're responsible for the product line itself. Then we have a small-scale flight software group, Microchase here, and a large-scale flight software group as well. And they're going to leverage the assets built by the core flight software group to actually create deployments of flight softwares to particular missions. So the core, again, this is really a feedback mechanism. As the large-scale and small-scale flight software groups utilize the product line and use the assets to create their flight software systems, the core group then strengthens its asset base and strengthens the product line with contributions and feedback from these groups. So when you're doing a particular deployment, for example, and you find a bug in the core, that bug is then communicated back to the core team, and then all projects using the core will benefit from the fact that one particular mission found that bug and the core team fixes it. So it's really an iterative and collaborative approach with the large and small scale groups. And then it's at the section level, has the responsibility of actually maintaining this product line. And so it utilizes the product line assets and all applicable JPL proposals. It deploys product line assets to project customers. It manages all updates required by projects using direct funds. Solicit funds via proposals to support strategic multi-mission capabilities outlined in the technology roadmap. This gets back to the kind of strategic vision of the section and where do we want the product line to go in the future. And then establish the process for continuous product improvement. Okay, so before I segue, I don't know how this thing works. Before I segue, so that kind of gives you the motivation and the objectives, as well as how we plan on evolving this product line over time. But now we're going to kind of switch gears, and one of the most important assets when you're developing a product line is the product line architecture. This is really the glue that holds the entire product line together and guides the assembly of a particular product from the assets in the asset base. So the architecture itself is one of the assets, as well as components, process, checklists, requirements, all those things I mentioned earlier. But the architecture itself is what you have to nail, right? That's what you have to get right in order to be able to create a coherent development approach and a coherent assembly of assets to create a particular product. So what we're going to talk about for the remainder of the presentation is the JPL flight software product line architecture. Okay. I think that one of the things that's important to recognize is that we're prescribing an architecture of a system as a whole, the flight software system as a whole. We're not talking about the architecture of the flight software core itself. That's a big distinction that I find when I give this presentation a lot of people seem to miss, is that we're not, we are going to go somewhat into the details of the flight software core and what the architecture of that piece looks like. But what we're really talking about is what is an architecture of the flight software system, okay, of which the core is just a small part. So keep that in mind as we go forward and talk about the architecture. So architecture objectives, the ilities, the quality attributes, the things, the properties we want our system to exhibit. First, and these are in kind of a ranked order. Number one, I mean, and I think this was obvious from Gerard's talk yesterday, reduce complexity. MSL, if nothing else, was extremely complex. And if we can attempt to reduce complexity through the application of rigorous architectural principles and constraints, that would be a huge win for us. We've kind of, the current architecture that was used on MSL, as I mentioned in my presentation at last year's workshop, we've kind of pushed the limits of complexity that we can handle with the current architecture. And so we need to really migrate the kind of Pathfinder MER MSL architecture into a new architecture that is able to handle the additional complexity introduced by mission objectives and the underlying hardware. So this is definitely a big ticket item for us. Reusability, this is kind of what this whole thing is about, right? Significantly improve the reuse potential of the standard portions of the flight software. Leverage existing flight-proven implementation approaches and assets, and reduce the flight software startup time and costs on a project or task. Reliability and predictability. We would like to have a property of deterministic execution and the robust execution of critical software functions in the presence of faults in non-critical and non-interacting critical software. That's a really important point. You want to be able to predict the behavior of the system as a whole. And with the ever-increasing amount of complexity in today's spacecraft systems, one of the issues that you have is emergent behavior, that you do not necessarily know how the system will behave as a whole until all the parts are actually together working as one. And so if we can construct the software in a way that we have more deterministic execution and more predictability, then we can assert certain properties about our system that we were not necessarily able to assert on past missions. Testability. There was a tremendous amount of effort in the V&V program on MSL, so we want to reduce the V&V burden of the projects. How do we do that? Availability. We want to increase the availability of our flight software. In other words, you want to be able to reconfigure the system, for example, to load and execute the minimum set of critical software functions so that you're minimizing your downtime and increasing the time that your system is available for keeping the spacecraft safe. Maintainability, in particular, extensibility and modifiability. Extensibility is important, especially on our Mars missions, where you're not really actually dealing with a single spacecraft. You're actually on MSL, as I've mentioned in previous talks, you're talking about 4 different spacecraft. Okay? MSL is a cruise spacecraft, it's an EDL spacecraft, it's a robotic arm, and it's a rover. That's 4 different spacecraft in one vehicle. And they all have different applications in different mission phases. You want the ability to extend and modify your software to fit the characteristics of a particular mission phase. And we want to create an architecture that allows for that capability. And finally, portability. This is kind of an important idea in terms of technology infusion and product line evolution. We want to make sure that the flight software is portable to multiple different platforms. So reference bus, for example, maybe eventually a broad reach box. We want to, as missions evolve, we don't want to close off any avenues of applicability, so we want to make sure that we keep it portable. And of course, support for software executing in different partitions, CPU cores, or processors. So these are our driving architectural objectives, and based on those architectural objectives, we came up with the JPL Flight Software Product Line Architecture. So in this diagram, you see a representation of an entire flight software system. So a flight software system in this architecture is a combination of this flight software core plus apps. One of the analogies that we like to use when talking about this flight software product line architecture is your iPhone. Okay? So you have an iOS, and then you have a bunch of different apps that are written and are pluggable into your iOS. It's the same concept here. You have a flight software core, and then you have apps that you can plug into that core based on the standard API and interfaces provided by the core product. This is a component-based architecture that provides architectural separation of fundamentally different concerns, so mission-critical versus non-critical functions. So this layered component-based architecture is the architectural tactic that was used to address the architectural objectives of improving reliability increasing development flexibility, and improved reusability. So let's talk about the different layers and the different types of components. So this is a traditional 3-layer architecture where you have the functional layer at the bottom. The functional layer includes the flight software core, which we'll talk about in greater detail on a subsequent slide, as well as software services and device managers. Components that exist at the functional layer export a functional interface that provides discrete actions required to achieve spacecraft objectives. So for example, this is the layer at which you would see a device manager that allows you to, for example, flip a switch, okay? Create a data product, send telemetry, receive command. These are very basic, primitive, discrete actions. Built on top of the functional layer is the activity layer. And so components that exist at the activity layer in the architecture export an activity interface. And an activity interface is what you would normally interact with from the ground. And activities consist of a collection of these discrete actions provided by the functional layer to achieve certain spacecraft and mission objectives. So something you may see at the activity layer, to use an MSL example, would be do EDL, entry, descent, and landing. And then that activity decomposes into a set of functions exported by the functional layer. At the behavior layer, you have a collection of components, or one or more components, that export a behavior interface, or are the components that are responsible for coordinating the behavior of the spacecraft. So they're responsible for coordinating activities. So the types of things you would see at the behavior layer are things like fault protection. Okay, your spacecraft mode management, your spacecraft configuration, your communication behavior, wake up, shutdown. These are autonomous behaviors that are used to achieve mission goals. So again, this is really this kind of traditional 3-layer architecture where you have your reactive layer, your deliberative layer, and your autonomous layer sitting at the top. And then within each layer, discrete components. And, oops, what did I do? This is somewhat of an eye chart, but as I mentioned, at that functional layer, we have a very special product called the flight software core. The flight software core is the component that interfaces directly with the underlying compute platform. It provides the execution interface for other components. So the core component provides the functionality necessary to support the execution of a component on the target compute element, as well as the interfaces to key spacecraft capabilities, including command, telemetry, timekeeping, reliable data storage, and basic input-output. So the core component abstracts the underlying computer from the remaining apps. So internal to the functional layer, so this is kind of a blow-up of the functional layer, you see there's this flight software core, and then perhaps in a flight software system you would have other software services and other device managers. The functional layer itself is layered, okay? So at the bottommost layer of the functional layer is the platform abstraction layer. And this is where you actually have your interface to the underlying RTOS, whether it be VxWorks 6.7, VxWorks RTPs, VxWorks 653, an OSAL, which we call Core OS, which is the abstraction of that RTOS, and a set of device drivers and your platform interface software. So this is your SUROM, your board support package, your any abstract device frameworks that you may have. So this layer is what interfaces with the underlying hardware itself. And the reason we did this is because we want, as I mentioned before, we have this reference bus, which is really a suite of avionics boards, and we want for a particular mission to be able to change the configuration of those boards and the combination of those boards. So depending on what deployment we're making, we can change only this platform abstraction layer to deploy the core onto a particular configuration of reference bus hardware. Okay? Built on top of the platform abstraction layer is your operating system services layer. So this is your basic operating system services, okay? These are things that really aren't going to change from mission to mission. This really should stay and remain the same depending on what deployment you do. And this includes your messaging code, memory allocation, basic utilities, timekeeping, and your basic input-output. And then at the top layer of the core component, and at the top layer of this functional layer, it's also where these software services and data device managers live, are your spacecraft services layer. This is a set of services that the core team determined are pretty much common between from mission to mission. So this is command, telemetry, parameter management, health services, okay? These are things that we see from mission to mission are pretty standard, are pretty common, and so we're putting them internal to the flight software core to provide for a particular mission. But the idea being that this layer is much more tailorable from mission to mission, which is why it sits at the same layer as independent software service and device manager components. So for a particular mission, for example, you could imagine that they have created a very special command interface, for example. So the idea is that you could actually take this command portion out of the flight software core and roll your own command service. Now, we don't necessarily recommend that, but we are saying that that is kind of the capability provided by creating this much more layered approach internal to the functional layer. So to give you an idea of what a real system looks like, I know this isn't it's not very illustrative. It doesn't have, like, as you can see, the boxes are different sized because I had to pull the module names out of the boxes to make it ITAR happy. But this gives you kind of an idea of what MSL would look like if we would have organized the software in this fashion. You see a much more simply organized system where we have, I think there's maybe 15 components or so in this system. You have the core component down here, electrical power system, your GNC device managers, your GNC software services. We see that, for example, you have your CEDL activity, cruise EDL, separate from, for example, your surface mobility component. And then at the very top, we have our system. We have one behavior, our system behavior, and this includes things like fall protection, comm behavior, wake-up shutdown, spacecraft modes, and spacecraft configuration. So this is a greatly, I mean, if you guys remember my presentation from last year, you remember kind of the module soup that was the MSL architecture, and we've now componentized it, right, and organized it into a set of components and layers to make it much more intellectually manageable and understandable. Okay, so that being said, so now we know we have a layered Componentized architecture. Well, what is a component? A component is I would say, a logically cohesive set of software functions that export a well-defined interface and follow a standard design pattern. And the standard design pattern is what you see here. You have a single master control thread. You have one or more real-time threads. You have one or more non-real-time threads, or 0 or more non-real-time threads. A standard set of queues, a control queue, a reply queue, a request queue, and a command queue. You export a standard component management interface to the core. So the core is able to set the component state or get the component state, and also it has a command to execute a thread. And then here is the set of other interfaces. So for example, the functional layer components export functional interfaces, layer components export activity interfaces. And then you may or may not have a shared memory region which has the single component writer and multiple component readers. It's important to note that the JPL flight software architecture is both space and time partitioned. So what you see here, this particular figure kind of leads you to that conclusion, right? Because you're running rate group threads, and you also have this shared memory region. This kind of gives you clues that that's the direction where we're going, but I thought I'd just state it up front that what you're going to see throughout the rest of the presentation really speaks to our ability to space and time partition the software. So components only communicate via asynchronous, non-blocking messages from a single sender to a single receiver, or synchronous access to a single writer shared memory region. So what you see here is the core component. Okay, and here's an activity which is going to send a message out from its outgoing queue into a request to the core. Similarly, another component, a device manager, can send a message to the request queue, and that's how these components communicate with one another. Okay? It's important to note, again, for space partitioning, that these are actual data structures. They're not pointers. So we're not passing pointers. We're actually passing the structures themselves. Similarly, to support space partitioning, you have a read-only access to a shared memory region. So this is intended for data that, for low latency data retrieval and for passing of very, very large sets of buffers and sets of data. All components also implement a standard component state machine. Getting back to our architectural objectives, this is a tactic that enables predictability, predictable behavior, and supports reasoning about system state. So every component that followed that standard component pattern also has a state machine built into it. And each state has very well-defined characteristics. So you can be in the uninitialized, stopped, started, or failed state. And then there's different characteristics of the component based on what state you're in. So when you start up a system, you come into the uninitialized state. And this portion of the mission, your non-volatile and volatile states are both uninitialized. You have no threads running. Your queues have not been established, and you're not sending messages. Then a component is spawned, and you transition to the stop state, where you restore your non-volatile state. You initialize your volatile state to a known boot state. You've spawned your threads, and you've established your queues, but you're not actually processing any incoming requests. It's not until the core component tells you to go to the started state that you begin processing these incoming requests. The failed state is a special state. As I mentioned before, one of the properties we wanted to see out of our system was availability, right? And as Gerard spoke to yesterday, what happens, for example, if you were to hit an assert in a piece of instrument code? Well, what would happen is you would actually take an entire system reset. So the system would go down. The idea here is that in a space and time partitioned system, what you're now capable of doing is transitioning that instrument component to a failed state and then continue to process and continue to run the rest of your system. So by separating your non-critical functions from your critical functions, adding the protection of space and time partitioning, you can actually transition a component to a failed state and continue your mission. So you're increasing system availability. So that kind of gives you an idea. That was really the structural view. Okay, like what is a component? What is it comprised of? How does it communicate with other components? But now we need to talk about the dynamic view, the execution architecture. How does this thing actually all hang together, right, when you have a set of components? So as we mentioned before, this is a space and time partition system, and one of the properties and principles of our architecture is that there are no compile time dependencies. Associations between components and the core are established all via registration. So the software, this allows the software to, components to be integrated into the flight software system without any changes to the core or any changes to unrelated components. So these components truly are standalone, okay? And that's a huge, that's huge, right? Because this is going to increase our ability for independent development and delivery. How does that work, though? And this sequence diagram shows it. And I apologize for this sequence diagram. I blame Magic Draw. It's just so tiny. But I can walk you through it. So your SUROM basically tells the core component it's time to boot up, time to go. So core component itself is going to go through its initialization. It's going to start, and then it's going to start the process of loading components. So it's going to go to its non-volatile memory and say, okay, what components have been registered with me, okay? And let's say it finds, 2 components. So it's going to load that dado from non-volatile memory and spawn component X's master control thread. That master control thread goes through its own initialization process where it actually spawns off its rate group threads, okay, and binds the standard set of message queues to the master control thread. That's the initialization process. It then is going to register with any services that are utilized by the core. So that could be things like commands, telemetry, parameters, all of that information. Typically, that couples the underlying operating system, core services with a particular component that's all done through registration now. So you're really decoupling the core from the other components in the system. And then it's going to basically tell the core, hey, I'm done, I'm ready, I've done everything I need to do to get to the stop state. I'm here, I'm ready to go, and the core is like, all right, start. And it sends a component to tells the component to start. And then it goes and it loads the next component and follows the exact same process. So the entire system is brought up in this fashion, and by the end of your initialization process, you have the core component running with a set of registered components that are all completely independent of the core. Once that finishes, then you start your typical execution. And this is where we get into our rate group execution architecture. Components segment their real-time processing by rate and create separate threads for each rate group. So you see that here. You see the master control thread and then a thread for each rate at which, this is just an example. This just says 64 hertz, 8 hertz, background processing. It really depends on your system. But you have a thread for each rate group. The real-time processing execution schedule is set. It's fixed at system initialization. This is a tactic used to support the property of deterministic execution, which we talked about earlier. It's important to note that one of the reasons why this is a principle in this architecture is because we are time partitioned. And in strictly time-partitioned operating systems, such as ARINC 653, the schedules are fixed at system initialization. Okay, so it's partially driven by our movement to a time-partitioned system. Furthermore, components segregate their non-real-time processing to separately dynamically scheduled threads. So one of the capabilities you have in time partition system is to actually use up the slack time in your schedule to schedule non-real-time processes, to schedule background threads. And so we put that processing on their own separate threads that are dynamically scheduled. All critical processing, however, is done on real-time threads, and we define critical processing to be a set of functions required to maintain vehicle health and safety, including hardware safety and minimum communication, command and telemetry with the ground. Again, the main critical component in our system is the flight software core. Rate group, the rate group execution architecture is a very flexible approach to scheduling. Not all applications need to implement the full set of rate groups. Part of the configuration of a component is to identify which rate groups it requires. And an application that doesn't require a particular rate group obviously wouldn't expend any system resources on that rate group. Furthermore, the architecture does support non-critical event-driven processing. Not all processing must be done in rate groups. Non-critical processing may be done on aperiodic threads within the component. These threads request time slices for the core for execution. This is the dynamically scheduled non-critical processing I was talking about earlier. And the core then adjusts the schedule to allocate time to these threads. This allows a non-critical application to not use rate groups at all. You could have a completely non-critical component that doesn't have any rate group processing and does everything on background threads. Another feature of our architecture is that we have a very strong concept of supporting patterns. So components follow a set of key supporting design patterns such as device, power, and health states, and fault monitor behavior to support behavioral predictability. So again, these are just kind of eye charts, but what you see here is these two figures right here show our fault monitor pattern, how the colors actually work, and what is the logic for evaluating a fault monitor. You can't really see the details. I basically just put these up here to illustrate the fact that we have these patterns and that all monitors in our system would follow this particular pattern. Similarly with device state. One of the lessons we learned on MSL was that standardizing device states and monitor states and following these patterns really helped us to understand the behavior of our system better. And so we wanted to freeze these patterns early in our architecture such that any components that are built follow these patterns. It just makes it so much easier to understand the system behavior if you can predict how a particular device will behave. So we use these supporting patterns throughout the architecture and expect our component developers to follow them as well. So if we take a look back at the architecture objectives that we had, I think you'll see that we've really achieved what we've set out to accomplish. A great reduction in complexity by a very strict layering and componentization rules. Reusability. The core component itself is highly reusable from mission to mission and can be deployed and configured for a particular reference bus application. Reliability and predictability. Our movement to a rate group execution architecture, as well as a standardized component state machine, really achieves this idea of reliable and predictable system behavior. Testability. Because we're space and time partitioned, you can test the individual components by themselves, and then system V&V then becomes an effort of assembling and testing already verified and validated components. Availability, you can now have component level fault protection on your software, where you can, transition a component to the stopped or failed state and maintain system availability in the presence of faults in non-critical software. Maintainability is incredibly increased because of our componentization. You can replace components with another component that exports the same interface, and you can expect it to have the same basic behavioral features as other components because they all follow the standard component state machine. And portability. By creating that platform abstraction layer, we're creating a very portable flight software core that can be used across multiple reference bus deployments. So in summary, the JPL flight software product line helps us address key issues, provides a means of consolidating flight software infrastructure development. It allows flight software components to be tightly coupled to their subsystems associated with the organizations they represent while minimizing the coupling with one another. It offers a consistent approach for costing flight software on future missions, and it provides a more direct path for flight software technology infusion into flight projects. And so with that, I'd like to open up for questions. Oh, look at that. I nailed it. 1 hour exactly. Yeah. Go for it. Oh, there's a microphone. Oh.
It's carefully hidden.
Oh, okay.
Very good. Who was it? Oh, there you go.
Hi. Is this on?
Well, it takes two software.
It's a physical switch. Oh. Scott Miller from Northrop Grumman. I've got 9 items I'd like to talk to you
goodness.
about. So I'll just keep this. But let me just take it down to 2 things. One, my 2 cents. Reuse has been a grail that our upper management has been chasing forever, and it's never worked, except on certain small instances of programs. And I think what really comes down to is coupling to interfaces, and whether that's down to the processor or the RTOS employed, or going out onto a bus, whether we're using SpaceWire or 1553 or something. So if you solve that, then you can get there. If you don't, then you're totally sandboxed on your particular program. But it's an admirable endeavor. But I'm just wondering, in terms of organization, you've got this really line-centered product. How do you represent that in the programs? Do you have representatives in programs, or do you have points of contact? Because if you're supporting this and you have either a bug or an enhancement that's been put into, or the bugs should be taken out of, not saying you're putting them in, but you've upgraded the core components. How do you roll that out? How do you organize that?
That's a great question. So one of the things that we've kind of our baseline approach to this is that each project is going to have something called a deployment KAGI. And they're a representative from the core team that is assigned to a particular project. And it's their responsibility to work with the flight software systems engineer to determine if any changes that are rolled into the core, if those are actually should be deployed onto a particular project. We also have something called the Flight Software Core Change Control Board. And it's the responsibility of that change control board, not the responsibility of the project change control board, to determine whether or not a particular fix is rolled into a point deployment of the core, or if it's rolled into the product line itself. And so we're really taking, I mean, I hate to go as strong as to say this, but we're taking the power out of the project's hands and putting it in the line and saying it's the line's responsibility, it's the core flight software group's responsibility to make educated decisions about where they want the core to go.
Any other questions?
I've got a lot.
I'll be the last one.
Okay.
Mark Reed from Johns Hopkins Applied Physics Lab. I had a comment and a question, or maybe two questions, I don't know.
Sure.
First, I know a lot of people at APL are excited about working on Europa with you guys.
Yay.
So
are we.
And I guess the question maybe is, you said early that this is a cultural shift. And we went through this about 5 years ago at APL, taking our messenger and stereo architectures and migrating them toward Goddard's core flight executive and repackaging in this layered approach. Have you experienced any pushback from, I mean, we got a lot of pushback from people at APL saying, you know, it ain't broke, don't fix it.
Right.
And I want to know how much pushback you've gotten and, you know, what your experience was there.
That's a really good question. It's funny because I'm going to answer this question 50-50. I would say 50%, I would say pushback is an understatement, and 50% we've gotten tremendous support. So it really depends on who you talk to and what camp they're in, right? But we have gotten a lot of pushback in terms of, you know, there are some missions that we currently have under funding that are essentially build to print. And we've gotten some pushback from those missions basically saying, well, we don't need this. Why do you know, we just landed a $2.5 billion spacecraft on the surface of Mars and it worked. Why are you trying to change it, right? On the flip side of the coin, we have another group of upper management that is very much like, this is absolutely the direction we should be going. We need to institutionalize our reuse approach. There are new software technologies such as space and time partitioning. We need to move in that direction. We need to be able to deploy on new processors. So it's a double-edged sword. Definitely feeling the pull from both ends of the spectrum. So.
And I guess the follow-up comment is, looking back at APL, that 5 years, it's well worth it. The work you're doing is going to be well worth it. You guys are going to be in a much better place 5 years from now than you are today.
We certainly think so. Thank you.
Boris Lipshin at MIT, but formerly of SpaceX. And SpaceX moved to, I was a big proponent of pushing SpaceX to like a component-based GNC architecture, and there was quite a bit of pushback from that as well. And what we found the trade was you win a lot in flexibility, but you do sacrifice this, you know, the very nice secure interfaces that would be checked by a compiler for you. And so as interfaces shift in the development of a project, you have to be very careful in making sure that you have to, you know, update all your components and stuff like that. And you sacrifice a little bit of that reliability that the compiler would give you. And I was wondering if, like, you know, the format of one of your messages would change. What would you have to do to fix that?
That's a good question. So one of the things that we've spent a lot of time with the Flight Software Core is actually fixing our API. So we spent almost the entirety of FY13 in pretty intense design team meetings coming up with a generic API and a generic interface to the core so that we are we believe we've reached a point where the API is not going to change. It's going to be fixed, and we kind of have, you know, touched all bases. Now, that being said, invariably, you know, the devil's in the details, and once we actually start doing deployments and you know, using the core in a variety of applications, we're invariably going to find that our API is going to need to change. But through configuration control of the API, we're hoping that problems like you mentioned will be mitigated, in that if we make a change to the API, we're going to have to notify component developers, hey, this API changed, update your interfaces. We've done our best at approximating what we think the API should and will be, and we want to keep that fixed, and it's going to have to go through CCB if it needs to be changed. But because of the strength of the interfaces between components, I really don't believe it's going to be a problem.
Okay, thank you.
I heard you mention OSAL, and I was wondering if that is the one that is currently out there developed by Goddard, or if this was something that you've completely developed yourself.
No, this is JPL's OSAL.
And so this entire effort was something that JPL has developed from the ground up?
That's correct.
Okay.
Hi, Kevin Scharf, PDR. So I worked on a product line with several million lines of code for several years, and the problem that we had there was that there was no consistent ongoing funding source for the product line itself. It was only allocated through the particular programs, and as those got constrained, then they would tend to let things lapse as far as dependencies, and those things would start leaking through. And I was just wondering if what sort of funding source you have ongoing to avoid those sort of problems.
Yeah, currently, so we're actually right now in the process of establishing what our funding source is going to be. Right now, the core flight software is being funded from the directorate using direct funds, or burden funds. So we are project independent right now, but the idea, we're kind of throwing around a bunch of different funding source ideas, whether that be, like, for example, putting a tax on flight projects, or creating something like a service center, or billing projects directly. We haven't ironed that out yet, but I agree with you, that's a huge challenge we're facing right now, to figure out how we're going to keep the steady stream of funding coming so that we don't run into those problems. Maybe next year I'll have an update for you on that.
That'd be good.
Orhan Uğurlu from Turkish Aerospace Industries. I want to ask, you have shown different views of the components, allocation of the components to different views. What about, you mentioned time and space partitioning? Mm-hmm. How you allocate those type of components to different partitions? Is there?
So right now our approach is a single component per partition. So,
thanks.
Yeah.
I'm Alayo at JPL, but I had, what projects is this being used on?
So right now, the flight software core is being proposed on any future proposals that that Section 349 is proposing to. We are also baselining, or hopefully baselining, on Europa mission. The software engineer on Europa is basically setting up the architecture to use core. That, of course, is still a long ways off. And right now, the big thing that we're targeting, we're in talks with Mars 2020 to figure out what the approach for Mars 2020 is going to be. We are, of course, pushing core, but that decision still has not been made. So right now, we're just in proposal stages for all missions.
And I had one question about slide 15, if you don't mind.
Okay. I can figure out how to use this. 15.
So in this slide, you have an uninitialized state, a stop state, a started state, and a fail state. And the stop, started, and failed generally have very explicit, so the behavior is sort of explicitly known. But the uninitialized state, sometimes you can have situations where the explicit behavior is, it's not obvious. Mm-hmm. I just wanted to know if you could speak to that. So,
can you give me an example?
For example, right? If you have a car, right, an uninitialized state, would be the car's off, right? But the car can also be in park or neutral, right? And so in a spacecraft, for instance, if a spacecraft is in uninitialized state, so the question then is for maybe someone on the other end is, what really is the state of the vehicle? Is it actually doing anything?
Yeah, it is not doing anything. Uninitialized really is a landing point. It's almost like a transient state that you pass through in order to get to the stopped state. So it's really kind of the point in between. I've loaded the .0 and now you've essentially loaded the .0. That's pretty much it. Yeah.
Other questions? Okay, me.
Okay.
So I'm interested in change control, but I'll save that for later.
Okay.
Is there a move to make this policy at JPL, mandatory policy?
Yes, there is.
How are you doing that?
Yeah, there's a very large movement to make this the policy, and I think it really boils down to the support from our line management and our upper division and directorate management. We have, as the gentleman over here, was asking about, have you gotten pushback? And I said, well, yes, there's some pushback, but there's also a lot of support. We have support all the way up to the directorate level at JPL, at the ESD level, and they are really basically pushing this to be policy, that this is our flight software product, and this is what we're using, in the future. Now, it's really going to come down to where the rubber meets the road, when Mars 2020 has to make a decision. And I think that we will see the power of the line come through in those decisions as we propose to new projects and as we try to baseline on funded flagship missions. That's where we're really going to see the power of the line come through to make this policy at JPL. So it's really a grassroots effort. I give, some days I feel like my job is giving presentations. But it's just trying to build support from the ground up, explaining to people, what are the benefits of using core? Why would you want to use core? And spreading the word. That's really I guess my answer is it's a grassroots effort with a lot of upper management support.
Eventually, there's a place for a dictator.
Yeah. Yes, I agree.
I think this was very good. Are there any other questions? I think this was outstanding.
Thank you so much.